Hello, this is Douglas McDougall here at the Maple 2021 conference. So let's get started talking about the mysteries of Babylonian astronomy and how I explored it with a very simple Maple software program. I had read how amazingly accurate the Babylonians were in calculating the synodic periods of the outer planets. So I decided to simulate it and test it. So let's talk about what a synodic period is first. If you imagine the sun, the earth, and say Mars all in a line, that's called an opposition. At that point, that's when the planet rises at sunset and it is overhead at midnight. And for Mars, this occurs about every 2 years and about 50 days. If it were exactly every 2 years, Mars would be in the same place in the sky every 2 years. But the extra days means that Mars shifts position around the zodiac with each return. So you can see on this chart how that could work. This is a picture with the sun in the center, the Earth in the next ring out in blue, and then Mars, the third orbit out. And you can see that in October 2020, the sun, the Earth, and Mars were all lined up. And you'll also notice that it'll take about a little more than 2 years, December 2022, for the next opposition. And the arc that makes during that time is called the synodic arc. So its near return to the same place in the sky occurs in a little more than 7 cycles. And you can count those on this diagram. But the Babylonians wanted to know exactly how long it would take for the planet to return to the same place in the sky. Not the same constellation, not nearby, but precisely the same spot. And they devised a very clever means of doing this. They figured out how many days and years exactly when a planet would return to almost exactly the same place in the sky. So I wanted to figure out how the Babylonians did this. All the literature says it's done. They did it through observation. I wanted to test it mathematically to see how they were able to achieve it. And I took Mars as the example because of its recent opposition a year ago, because the Babylonians gave special significance to Mars, and I personally have always been fascinated by the planet Mars. So let's look at the historical context, and to put you in the mood, this is the lion at the gate of Ishtar and the processional way in Babylon, very famous image. This is from the Metropolitan Museum of Art. So the intriguing part here is that in Mesopotamian cosmology, it was the gods that determined everything. They determined the planetary movements. Every time the planet moved this way or that, it was the will of the gods. So it was very profoundly illuminating to them to determine both the regularity of the planets and any irregularities that they detected. Because that would be an indication of divine intention. So from the mid-7th to the mid-1st centuries BC, it's a phenomenally long period of time, the Babylonian astronomers kept meticulous records, and they did these on clay tablets and in cuneiform writing in the language of first Sumerian, then Akkadian. And it's truly fascinating and amazing to me that anybody could look at a tablet like this and be able to decipher not only words, numbers, but actual underlying astronomical meanings and theories. It took almost a century to do that with a phenomenal amount of intellectual effort, mostly by intrepid scholars copying every stone, every tablet they could find, and then working hard with linguists and astronomers to decipher it. So among those tablets, there's a set of them called the astronomical diaries, and they accounted for the synodic phenomena, including other events, like they linked these phenomena with events like commodity prices, the level of the Euphrates River, and any local news that was at hand, because they wanted to know whether, again, the divine intention of the gods was to give an omen if a planet did a certain thing at a particular time, and that happened to be a time when a king died or a flood occurred or a good harvest occurred. That was noted so that they could sift through and make sense of all this. Of course, the eclipse mythology was famous in Babylonia because it often signified terrible things were going to happen to the king. So Mars itself, along with Saturn, were regarded as having a malefic influence. They had ominous characteristics, and so it was of particular importance to know when it would make its return to the same place in the sky. And so scholarly examination of these tablets yielded quite a few interesting surprises. They had figured out, the Babylonians had determined the synodic periods with incredible accuracy. And they called the planetary returns that occurred within 1 century, they called them goal year periods. And if you read anything about Babylonian cosmology, Babylonian astronomy, you'll probably run into the term goal year periods. And for Mars, there were 2 that occurred within the 1st century. Within 1 century, there were 22 synodic cycles. In other words, remember that chart where it went around all the way around once and came back and then had to overlap because the 50 days didn't quite match up. But in 47 years, they matched up quite carefully, and that was in 22 synodic cycles. And in 37 cycles in 79 years. So those were the 2 goal year periods. So I wanted to see if these goal years, which were again determined by observation, were mathematically determinable. In other words, were they inevitable mathematically? And how quantitatively accurate were they? And were there other possible choices? Did they pick the best of a range, or did the mathematics lead to the only conclusion that those were the 2 goal years in a century? So Maple is, of course, an exceedingly useful tool to do this kind of things and for quickly testing assumptions, because if you read the scholarly literature, there's all sorts of conclusions that are made, and I'm always wanting to poke holes and test it. And I use Maple as a kind of notebook at my side, and it's very handy. So in this case, we have the classic case of new meets old. There is a rather wide range of years between Maple programming and these cuneiform inscriptions. So using a very simple Maple program, I wanted to find out what happens when the Earth catches up to Mars every synodic cycle. So these were simulated for 100-year, the normal 1 century period, and out of curiosity for the 500-year periods. Of course, finding an exact recurrence period for Mars will be impossible for the same reason that an irrational number can't be reduced to a simple fraction. You can see that in the next slide I'm going to give you, that just 80 years of Mars data traced from the NASA JPL website leads to a very interesting pattern that does not tend to repeat exactly. So, and you'll see in the center is the Earth. The little orange dot at about 4 o'clock is Mars at its 2003 opposition, and the little darker blue dot off to the right, maybe at 2:30, on the clock is Mars at its last 2020 opposition. And you can see that these traces of its orbit, which were inspired, by the way, by an orbit diagram Kepler did of using about 16 years of data from Tycho Brahe. You can see that this is not going to be easy to determine just from intuition exactly when Mars is likely to return to the same spot in the sky. This Japanese basket pattern, gets even more complicated if you plug in more years. So again, if you can't find an exact recurrence period, one can do it within any chosen margin of error. And so the Maple program, I cooked up, searched for oppositions that were within a few days of being exact recurrences. And then I filtered out the rest. So with using only the length of the synodic period that I gave you and the length of the Earth year, the program displayed the same best cycles in 1 century. And you'll recognize that those are exactly the Babylonian cycles, for the goal years, I should say, 22 cycles in 47 years, 37 cycles in 79 years. And those are exactly the same known from about 400 BC with the Babylonian astronomers. So after 22 and 37 synodic cycles, Mars will be very near in the sky where it was at whatever point we decided to start our observation series. So near isn't exact. So, and the Babylonians knew that those goal years were very accurate, but not exact. So I wanted to know how accurate they were, and the program found what I called the day variances, meaning what is the error, so to speak, in the number of days for Mars to arrive on station where it was before. And in 22 cycles, the error was about a little more than a week. And in 37 cycles, it was about 3 days late. So again, it arrives, and this is the same place in the zodiac. So if it's if it's in the constellation of Pisces, now then at the end of the goal year period, it will be in the same constellation, either a week earlier in the 22 cycle 1, or about 3 days late in the 37 cycle return. And the first thing that jumped out at me is that 37 cycle return is what Ptolemy was using in his Almagest, and he was using observations that were collected about 300 years earlier from Hipparchus, who himself was getting his data mainly from the Babylonians. And here's the fellow himself. I'm sure that's an exact image. So the variance is also squared with the cuneiform tablets that were collected at the end of the 19th century and interpreted by modern scholars. So now here's the fun part, very interesting cleverness on the part of the Babylonians. Or by combining goal year cycles to cancel out the errors, the Babylonians could, in effect, get even greater accuracy over longer periods of time. So, and that's been the scholarly hypothesis. I think it's reasonable. I wanted to do a quick confirmation of it. So my program showed that if you could generate, three 37 cycle returns and add it to a 22 cycle return, you get 133 cycle returns over 284 years. And how does that square error-wise? The minus 8-day variance for the 22 cycle is added to the 3-day variances plus 3-day variances for the 37 cycle, and you get a net error of 1 day, which is a considerable improvement over the 8s and the 3s. So over 133 cycles, you get 1 day error in almost 3 centuries. And the program confirmed the error value for that without using the summed error technique. So from a mathematical point of view, the result is expected. I mean, given the nature of periodic motion, the error from the first 22 cycle run becomes a starting line for the 32nd, 37 cycle run, and so on. So those errors aggregate and they can amplify and cancel depending on the combinations chosen. So I went ahead, just out of curiosity, 500 years, I was having fun. It's the what if kind of thing you can do with Maple. You can explore things very quickly in a way that scholars of old couldn't do. So we plotted sequences that were within 10 or days plus or minus of Mars's opposition. So in the following plot, you'll see the day variances along the y-axis and the synodic cycles along the x-axis, and the dots closest to zero are where the accuracy is greatest. And you can see on the left side of the screen there, the 37 cycle return and its 3-day error, and you drop down and you can see the 22 cycle return and its almost 8-day error. But notice if you go up to 133, the error is improved. It's closer to the zero axis, which means the x-axis, which means there is no significant delay. Notice if you go way out, and this is beyond what the Babylonians did, you can find things that are even more accurate. The 97 cycle thing came with a minus 2-day variance, and a 229 cycle, 489 return is good to about a minus 1 day. Again, longer than the Babylonians used, but and we don't know to what extent they were aware of these longer term possibilities, but it is clear that if you change initial conditions even slightly, those longer term projections change. And so they do appear to have settled on the 133 cycle, 284 year period is good enough for their prediction purposes, which basically meant their ephemerides. So as we've seen, a simple Maple program allows us to go back in time and explore phenomena that puzzled the ancients and to test accepted assumptions. So now I'm going to conclude with a few notes on the model, the coding that I used for the model. Remember, I started by saying it's an irrational number and you can't get an exact synodic period out of it. And so just in case you were skeptical, I printed out, this is 2.135, et cetera, years for each synodic period. It is a completely irrational number. Again, that's the mean number of years between Martian oppositions, the so-called synodic period. And remember, they were using essentially circles. Mars's actual orbit is an ellipse, so we say mean number of years. And they're also doing this over long haul, so it tends to even out. So each event is called a synodic occurrence. And so the first thing we did was we created a list of each synodic cycle in the set. And you can see down there 2.13, 4.2, those are sets of synodic, events in the number of cycles n. And then I used fraction to separate them out into fractions. And then I filtered the list to find elements that were within a desired distance, plus or minus, from an arbitrary epsilon from an integer. And then this is the filter I use, and I'm not going to dwell on this because I know you can call this up and do whatever you want with it at a later time. But essentially, I use the procedure to filter it out. And then I created a new set S with those fractional numbers. And with those, I centered them on 0 using another set of procedures, and then convert it into a list. And then from there, I wanted the positive numbers to represent when Mars was late. The negative numbers meant an early arrival. And so I had to link those also with the number of days, which I call day variances. And those, again, a different list of day variances. And then I wanted to zip them together with the hits and that new list. And by the way, this H is a list of the synodic cycles, and you can see it's 22, 37, etc. And I zipped those together with that function, and then came out with the total list. And from that, and you can see there's the -8 and the +3 right next to the 22 and the 37. Then I used point plot to display the results, and over 500 cycles that came in the chart you just saw. So I'm just going to quickly acknowledge and credit the following sources. Otto Neugebauer, his History of Ancient Mathematical Astronomy, and his Astronomical Cuneiform Texts are fantastic resources, obviously, for all scholars. Everybody cites him. Here he is at his desk. And also there's Alexander Jones, the people who have applied more recent technical methods to this. Alexander Jones at NYU and T. de Jong at the University of Amsterdam. So thank you very much. I've enjoyed it.